This presentation is part of the TI-Nfocus AP Calculus video series. In this video, I'll discuss a specific concept associated with the 2019 AP Calculus exam, free response question AB2, namely, a summary of particle motion analysis. My name is Steve Kokoska. I'm a professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Here's an outline of the information presented in this video. First, I'm going to present a summary list of common expressions and phrases used in AP Calculus particle motion problems. And then I'm going to translate each of these phrases into mathematics. I'll present and solve a particle motion problem in which technology is required, and then I'll leave a couple of examples for you to consider. Particle motion problems occur often on the AP Calculus exam, especially as a free response question. Many of these involve the fundamental theorem of calculus, displacement versus total distance traveled, and technology. I'm going to provide a brief summary of results associated with particle motion problems, and then a few examples involving these concepts. Let's suppose a particle moves along a horizontal line so that its position at time t greater than or equal to 0, is given by s of t, the velocity by v of t, and the acceleration by a of t. Here are some typical expressions or phrases used in particle motion problems, and the corresponding translation into mathematics. If we are given the position of the particle at time t equal a, this means that s of a is equal to b. The particle is at rest means the velocity of the particle is 0. The particle is moving to the right means the velocity is greater than 0. And similarly, the particle is moving to the left means the velocity is less than 0. The average velocity of the particle on the interval a to b is given by this expression. And remember that the antiderivative of the velocity function is the position function. The instantaneous velocity of the particle at time t equal a is the derivative of the position function at t equal a. And the acceleration of the particle at time t equal b is the second derivative of the position function, which is the first derivative of the velocity function. The velocity of the particle is increasing means that the derivative of the velocity is positive. And here's a similar expression in translation if the velocity of the particle is decreasing. And the speed of the particle is the absolute value of the velocity. The expression, the speed of the particle is increasing, means that the velocity and the acceleration have the same signs. The expression, the speed of the particle is decreasing, means the velocity and the acceleration have different signs. A common AP Calculus question asks students to determine whether the speed of a particle is increasing or decreasing at a specific time. Note that in both of these cases, the student can consider the derivative of the absolute value of the velocity, or the derivative of the speed. The total distance traveled by the particle over the time interval a to b is given by this definite integral, and note the use of the absolute value. The displacement of the particle, or the net distance traveled by the particle over the time interval a to b, is given by this definite integral. There's no absolute value on the integrand here. And the position of the particle at time t equal b is given by this expression, where s of a is the position of the particle at time t equal a. The particle changes direction means the velocity changes from positive to negative, or vice versa. And the particle is farthest to the left or right means that we need to find the minimum or the maximum value of the position function s of t over an interval. Now, a common method for solving this type of problem is to use a table of values. So we need to find the critical values of S and consider the position of the particle at the critical values and at the endpoints of the interval. Let's try an example that involves several of these concepts and the use of technology. Suppose a particle moves along a horizontal line. For t between 0 and 10, the velocity of the particle is given by the function v. The position of the particle is given by the function s, and we know the initial position of the particle is at -7. Find all the values of t in this interval for which the speed of the particle is 5. Write an expression involving an integral that gives the position s of t, and then use this general expression to find the position of the particle at time t equals 6. Find all times t in this interval at which the particle changes direction, and finally find the total distance traveled by the particle over this time interval. The speed of the particle is the absolute value of the velocity, so that means we need to solve this expression for t. Now, due to the nature of the function v, I have to use technology to solve this problem. Using the TI-Nspire, on a calculator page, I first defined the function v. Then I did some exploring on a graph screen. Here's a graph of the function v and the two horizontal lines y = 5 and y = -5. The x-coordinates of these points of intersection are the values of t at which the speed is 5. So I like to explore and visualize on the graph screen and then confirm my results on a calculator page. So here I used the solve command with a restriction on the value of t. So the speed of the particle is 5 at these two times in the interval 3 to 6. The position of the particle at any time t is given by this expression, and I interpret this as an application of the fundamental theorem of calculus. Note the use of the initial condition, and with the added emphasis on notation, note the use of the dummy variable x in the integrand. The position of the particle at time t equals 6 is given by this expression. Here's a graph of both the velocity and the position function on the same coordinate axes. And here I evaluated the position function at time t equals 6. And here's the confirmation solution on a calculator page. In part C, we need to find the times at which the particle changes direction. So for me, first, a little exploration on a graph page. At each of these times, the particle changes direction because the velocity changes from positive to negative, or vice versa. On a calculator page, I can use the solve command, and I can get the exact symbolic answers. That's pretty cool. Well, okay, I guess I could get these if I used paper and pencil too. And here are the numerical approximations. And again, don't forget the justification in this question. The velocity changes from positive to negative, or from negative to positive at each of these values. The total distance traveled by the particle over the time interval 6 to 9 is given by this definite integral. And here's how I can find this value on a calculator page. And I can also visualize this result on a graph page. Here, the graph of the absolute value of the velocity, or the speed, is green. The definite integral, or distance traveled, is given by the area of the shaded region. And on this graph screen, I also found 6.743. So I feel pretty confident about that answer. Here are two examples that I'll leave for your consideration. And the first one involves an extreme thrill ride at an amusement park. The slingshot ride at Cedar Point in Sandusky, Ohio is a reverse bungee ride. It uses specially designed springs to propel a two-person capsule attached to cables. The velocity of the ride is modeled by this piecewise linear function, and at time t equals 0, the slingshot starts at 20 meters above the ground. Find the times at which the slingshot changes direction. At what time is the slingshot at its highest point? And how high is the ride at this time? And finally, find the total distance traveled by the slingshot over the time interval 0 to 20. This example involves a particle moving along a horizontal line and some analytical work. The velocity of the particle at time t is given by this function v. And we know that the particle is at position s equals 40 at time t equals 0. Find the time intervals when the particle is moving to the left. Find the displacement of the particle over the time interval 0 to 4, and find the total distance traveled by the particle over the time interval 4 to 10. Find all the time intervals for which the speed of the particle is at least 20. You might need a little technology help here. And finally, find the position of the particle at time t equals 8. I hope this video provides a nice tabular summary of the concepts associated with particle motion problems, a few AP Calculus type questions, and some examples of the use of technology to solve and visualize these types of problems. And just a reminder, there are lots of valuable resources on the TI website. There is material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.